My chairman, honorable guests, ladies and gentlemen, good morning. It's a very great pleasure indeed for me to attend this meeting. Today, I would like to present my paper, Experiment Teaching Design of High-Power Smart LED Driver based on Arduino. The others are Yingming Gao and Wei Dongquang. I'm the speaker Wei Dongquang. This speech is mainly divided into 5 parts, namely background, introduction, smart drive design, system performance test, experimental design, and conclusion. The first part is background introduction and some applications of Arduino. As a popular open source hardware platform, Arduino has been paid attention to by many universities. European and American universities are very popular to use Arduino as a basic technology for teaching and scientific research. Many domestic colleges and universities have carried out teaching reforms and curriculum construction based on Arduino to complete the teaching goals while improving students' innovation ability. Based on Arduino platform, Dalian Universities of Technology designed the basic experimental course of the Internet of Things, which enables students to quickly understand the hierarchical structure of the Internet of Things and cultivate their development and innovation abilities. Other colleges and universities also have corresponding reforms. The original intention of Arduino is to provide our students with an easy-to-use microcontroller to help them realize their designs. This experimental teaching systems combines Arduino with LED drive technology to quickly build an intelligent prototype system with sensing and network functions through this system. The second part is the smart drive design. The chip-level intelligent LED driver has demanding function and can communicate with the microcontroller through SPI, I2C, single bus, and other serial communication interface. Since Arduino itself provides a variety of serial interfaces, the intelligent driver can be simulated by combining the Arduino and LED driver, as shown in figure, in the form of Arduino plus high-power LED drive extension board. It has a strange ability to expand and easy to be extended to the intelligent lighting system. This part first is the design of high-power LED driver expansion board. We use Arduino UNO as the processor. The expansion board includes key input unit, LED indicator unit, and high-power LED driver unit based on constant current driver HV9910B. The key is used to adjust the duty ratio of PWM dimmer signal. The LED indicator unit consists of 3 straw heads encapsulated LEDs and displays the duty ratio of the current PWM signal with a combination of light or dark state. The content on the table is Arduino UNO pin used by expansion board. The inside pins into the throttle of the Arduino board so that the extension board can be placed above the Arduino in the installation front shown in the figure. DC power supply is adapted in the system. The positive pole is connected to the Arduino win slot through an extension board, and the negative pole is connected to the Arduino Gen D slot through another inserting pin. The input voltage range of smart drivers is 8 to 12 volt Digital pins 8 to 10 are used to drive 3 low power LEDs in the indicating unit, bright and dark, respectively, responsive binary numbers 1 and 0. Their light or dark combination can indicate a PWM signals with different data ratio. The following picture shows the high-power LED driver unit designed by BAG HV9910B can output 2 kinds of PWM switch signals with constant cycle and constant load level time to drive the step-down converters circuit as a BAG converter and operating in continuous current mode when the output voltage U out greater than the input voltage U in 150%. That is when the duty ratio of the switching signal is greater than 1.5. It is advisable to use the switching signal with constant low level time to avoid sub-harmonic oscillation. The switch signal may be transmitted by oscillating resistance RT setting RT1 and is connected to pin 8. The other end is earthed and the other end is connected to pin 4, which is switch signal with constant low to level time. By introducing jump provided into the circuit, the system can switch between these two switch signals, ensuring the stability of driving multiple high-power LEDs. Next is the determination of key competence. The sign indicator of the expansion board is input voltage UIN. When the range is 8 to 12 volt, the output voltage U out range is 3.5 to 7 volt. Output current I/O equal 315 milliampere. Rapid current is 30%. The components to be determined are current dictators, resistor R2, oscillation resistor R1 or R3, power inductive L1 in the switch converter circuit, field effect transistor Q1 and diode D1. Equation 1 calculates the galvanometer resistance. You get RCS equal R2 equal 0.62 ohm. Equation 2 is used to calculate the oscillation resistance. You get RT equal R1 equal 100,000 ohms. Equation 3 calculates the power inductance, where the inductance voltage is the increment of the inductance current and its corresponding time increment. From the following two pictures combined with equation 3, it can be obtained the power inductor L equals 333 microhenry. The system uses field capacitor IRF 840 and circuit diode 1N5819 as switching elements as shown in figure on the right. The PWM signal causes the FATQ in the step-down circuit A to switch between on and off, and the diode D to switch between off and on, so that the current A correlates in the current B switch between A and C to realize the voltage conversion function. In the LED switch is instantaneous, completed, synchronized with the PWM signal as shown in Column 1 in Figure B, but but affected by the junction capacitance. The voltage across the p-n junction cannot change sadly, and the switching state of the device always lags behind the change of the PWM signal. Only when the switching time 10 and 12 of the device are less than the holding time of the PWM signal can be state transition be complete, as shown in Code 2 of Fig B. If the frequency of the PWM signal is too fast, its holding time is shorter than the switching time of the device. As shown in Code 3 of Figure B, causing the device to always fail to switch state and step-down switching calculator cannot perform the voltage compensation function. The subpart is system performance test. First is the index test. In efficiency is equal to the ratio of output power to input power. For DC power supply, power is equal to the product of voltage and current. The input voltage and current are measured respectively. After the output voltage and current, the input power and output power are calculated to obtain the efficiency. As the picture shows, the effect of two 1-watt power LED driven by expansion board is higher than that of 1-watt power LEDs driven by expansion board. Look at the picture on the left. It shows that the efficiency is related to the pressure difference and the load, and the pressure difference caused by the load should be considered comprehensively to obtain the high efficiency. Look at the picture on the right. As output voltage changes, the output current is relatively stable with a maximum of 345 microamp and a minimum of 327 microamp, something similar than the term output current of 350 microamp. Next is the signal test. This picture shows the switch signal output by HV991OB and the corresponding diode positive voltage waveform at the input voltage of 9V and 12V. According to the measurement result, for low-level PWM signal with constant time, its spectral decreases with the increase of input voltage under the condition of certain load. This is consistent with the effect of the output voltage or input voltage on duty cycle of the step-down switch converter circuit. The field equatorial growth voltage waveform is complementary to the diode positive voltage waveform. The maximum voltage of the diode positive electrode varies with the input voltage and is seen as the input voltage. The output switch signal of HV991B does not change with the input voltage. This picture shows the corresponding relationship between the switching signal output from HV991B and the damped signal input from the panel of PWMD. Channel 1 is the switching signal and channel 2 is the damping signal. In damping, the switching signal output from HV991B is not output until the damping signal is at high voltage, but not at low voltage. The actual switching signal output from HV991B is the result of logic and operation between the dimming signal and the controller's switching signal. This experimental teaching system can meet the needs of comprehensive experiments of light source and light measure. And these three on PowerPoint. Just the first is high power LED dimming experiment. The program changes the duty ratio of dimming signal output by Arduino digital pin 3 by pressing buttons to achieve dimming of high power LED. The duty ratio of dimmer signal starts from 0, as the key is pressed down each time. The cycle increases the duty ratio to 100% in accordance with the table, and then returns to 0. At the same time, the light or dark combination of three low power LEDs on the expression board is changed accordingly. Measure the working current of high power LED on the different duty ratio. Draw the working current curve of duty ratio and working current. And until time they understand the relationship between LED working current and the dimming duty ratio. The second is observe explain the logical operation relationship between switching signal and dimming. Switching signal is non-dimming and dimming signal. The last is illumination control experiment. The GY30 illumination signal model of I2C interface and the intelligent LED driver consists of the intelligent lighting control system with on-off control stage. The program relies the illumination control of the working surface. The last part is the conclusion. The experimental teaching system of high-power intelligent LED drive developed in this paper can be used in the teaching of comprehensive experimental courses of light source and lighting specialty, to help students deeply understand the working principle of LED drive. The experimental design combines Arduino technology with lighting control technology, which reduces the difficulty of programming and enables students to focus more on experimental content related to system performance tests and illumination control. These are all my speeches today. Thank you for listening.